Hi, this video will cover section 4.3, examples 8, 9, and 10. Before we get to example 8, we are going to review some of the properties to condense and expand logarithms. So here we have three properties, and assuming, of course, that x and y are the arguments, the expression or the number variable that you take the log of, and we have here a is going to represent the base of the logarithm. So we know that a must be positive, greater than 0, but also a, the base, cannot equal to 1. And here we're going to let r, which will be here the exponent, r is also going to be a number. So if you have the log of a product, which is what you have here, the product is x and y multiplying each other, that could be expanded into the sum of two logs. So two logs adding each other. And what you do is you split the argument that you have here, x, you put x here, and then you put y on the other one. Then we have the quotient property. So if you have the log of a quotient, that's the quotient, x divided by y, you can expand it into the difference of two logs. So here, since y is dividing x on the left, that is the reason why you put a negative in front of it. That's how you know which one has the positive sign and which one has the negative one. The third rule, power property, you take this exponent, you bring it to the front, and the exponent becomes the coefficient of the logarithmic expression. That implies multiplication, so r will be multiplying the logarithmic expression. Remember, r is just a real number. We finished those in class. So I'm going to start example 8, and what we have here is two expressions. One of them is the log of 7 base 6 is approximately 1.09. And here I have the log of 5 base 6 is approximately 0.90. So using those three rules that we reviewed, we're going to solve this logarithms without the calculator by using what was provided to us here. So we have here the log of 35, and 35 could be factored as 5 times 7. So I will start by writing it that way. Log base 6 of the product of 5 times 7. So if I expand that, it will become log of 5 base 6 plus log of 7 base 6. Now, since the log of 5 base 6, we have the value here is 0.90. I'm going to substitute that with 0.90. Then for the log of 7 base 6, I'm going to substitute that with 1.09. And what I will get from there by adding those two numbers will be 1.99. And that will be the answer to that question. Now the next one, we have here the log of a quotient, that is 5 divided by 7. So here what we're going to use is log of 5. We're going to expand it using the quotient rule or the quotient property for logarithms, and that will be minus the log of 7 base 6. Now I'm going to substitute the log base 5 part with 0.90. And I'm going to substitute this part, the log of 7 base 6, with 1.09. Remember, this is subtracting. And then if we subtract those two numbers, we are going to get negative 0.19. Now the next one, we are going to use the power property. So we're going to take that exponent, bring it to the front. And now instead of being the exponent of the argument of number 5, it will become the coefficient of the logarithmic expression. Now remember, 3 is multiplying that expression, and we do have a numerical value for it. The log of 5 base 6 is approximately 0.90. And that will give me 2.70. Now for the next part, we have the log of 6 base 6. And so that one, we could use that rule that states that if the base matches the argument, that could be canceled out and the answer will become 1. For the last one, we have that the log of 1 base 6, that is equal to 0 because 6 to the power 0 is equal to 1. And in fact, the log of 1 of any base will always be equal to 0, because if we turn that into an exponential expression, it will be a to the power 0 is equal to 1. So now for example 9, we're going to go over the change of base theorem. And this theorem is useful because most calculators are only able to calculate the log base 10 or the natural log, which is the log of base e. And remember, you have those two buttons on the left side of your calculator. So now calculators can calculate any type of base, but if you couldn't, then you will have to use the change of base formula. And this works for any base, and so I'm going to be calling the argument the big number just because of the size of the font, and the base will be the little number. And so what we do is we change a base 10 or a base e, and we write it as the ratio of two logarithmic expressions. The natural log of x, the big number, and divided by the natural log of a, what I call the little number. Of course, these are letters, they're variables, but they could also be numbers. So let's do an example with numbers. So we had something like the log of 7 base 5, and the question was change the base. It will be the natural log of this number, 7, divided by the natural log of the base, 5. Now, this expression could also work, well, the change of base theorem could also work with a base 10. So this will be log of x divided by the log of a. So if I want to solve this one using log base 10, common log, it will be log of 7 divided by log of 5. Now we're going to answer the question here, which is find the log of 3 base 7 using the change of base theorem. And so the log of 3 base 7, we could find it two ways. One will be with natural log of the big number or argument 3 divided by the natural log of, and then we will get an approximation with the calculator. Now the way you will enter this on the calculator, you have to press the LN key, then of course number 3. If your calculator opens a parentheses, you must close it. Then you will use the division key. And then after that, you have to press natural log key again, and then the number. So what I'm trying to say is that you must have natural log twice when you enter it on the calculator. And do not enter it this way. Because that is not equivalent to this expression. That will be wrong. So don't do that. Now, just like we can calculate it with using a log base e, we could also use a base 10. So that could also be the log of 3 divided by the log of 7. And then, of course, we will get an approximation. So I'm going to find it with my calculator. And that will give me 0.56457. So let's say if this problem said round to the nearest thousandth, because the next number is a 5, then we will just round it to 0.565 if it was to the nearest thousand. If the question said round to the nearest 10,000, then it will be 0.645. The next number is a 7, so that will make this 5 a 6. So make sure that you read to how many decimal places MyMathLab wants you to round to. So I'm going to move on to the next one, and this one, I believe we went over this problem in class. The graphs are already there, so the function natural log of x and e to the x are inverses of each other. Therefore, they reflect across the dashed line that you see here, and that line is the y equals x. Just like we discussed in class, the domain of this exponential function is all real numbers from negative infinity to positive infinity, and the range is from 0 to infinity. We also have that horizontal asymptote for the exponential functions, which happens to be y equals 0. For logarithmic functions, in this case natural log of x, we have a vertical asymptote, which is the y-axis, or the line x equals 0. That is the vertical asymptote. We also know that the domain is going to be the range of the exponential, so it's 0, infinity. And the range is going to be the domain of the exponential function. Because since they're inverse functions, they're inverses of each other, their domain and range is interchanged. We also have here an x-intercept, which is the point 1, 0. And the exponential function does not have an x-intercept. In fact, it has a y-intercept right here, and that is the point 0, 1. So that is a review from what we did in class. Now the next slide, it has a summary of both functions, logarithmic and exponential. Logarithmic. And the range of an exponential is the domain of a logarithmic function. Here we have a horizontal asymptote, and here we have a vertical asymptote, which happens to be x equals 0, or is the y-axis, and here the horizontal asymptote is y equals 0, or the x-axis. And that concludes this video. Problem 11, example 11, will be in another video. Thank you for